Thanks for being here. Today I will talk about leakage from microarchitectural elements, and that's why I called the talk Microarchitectural Incontinence. I thought it might be a pun that I could use throughout the talk, but then again I thought people might be pissed if I do that, so I will not do that throughout the talk. I will start with a short demo, and I prepared something here. So I will open an editor on the left, and then you can see a terminal window on the right. Let's just switch to that window. And this is just a repository cloned from GitHub that I put there a year ago, and I will show you a nice small attack where I exploit some leakage. So first, I just built this tool from this subfolder, and I will run it with the command line from the documentation, like this. And while I do that, I will trigger keystrokes in the gedit window. So this is an entirely unprivileged process, and gedit is an unrelated, unprivileged process. Okay, so as you can see, this program just runs over this library. So you see a progress number there, and what it shows you is an address and the number of cache hits I observed on that address while triggering keystrokes. I will just pick one of those addresses and see how I can exploit this address. For this, I have a second tool. This is in a different subfolder. Yeah, okay, I tried this already earlier that day. And if I do that, let's see what happens. Okay, nothing. And if I switch back to gedit, every time I press a keystroke in gedit now, I see the exact timestamp, and this is accurate to nanoseconds. Okay, so this took me a few seconds to find this leakage. There's much more to find. You can even find in the GDK library, for instance, it does a binary search over a key translation table, and there you can even single out some keys. So this is really bad if you can find leakage with that little time. Okay. So let's start with the talk. So instead of incontinence puns, I will just give this other analogy. You know probably those water races. If you haven't done them, they are fun even as an adult. It's a lot of fun to carry water over a field and pour it into another bucket and try to not lose water while doing that. So the CPU basically also transmits data from one bucket to the other. But when we started with x86 computers, we still had an i386, for instance. Now we're at Skylake. It's 160 times as fast. The DRAM module capacity also went up. It's 1 million times the capacity, and at the same time, the manufacturing size went down. So try to do a water race at 160 times speed with tiny cups which fit more content. Probably it won't work. So if you look at microarchitectures, starting from Nehalem and now ending at Skylake, we see a performance improvement from each architecture to the next of about 5%. And this improvement comes from very, very small optimization, mostly caches and optimizations in single instructions that can now take some shortcuts. And every optimization that you have in your program or in your hardware that is dependent on data or the location of the access or anything like that means more and more leakage, and we can exploit that. So, who am I? My name is Daniel Gruss, and I'm a PhD student from Graz University of Technology. You can find me on Twitter. You can also send me spam emails if you like to, but you can also just ask me questions there. Side channels are not a software bug. Side channels exist although you've written the software in a sort of perfect way. Of course, you can write software in a side channel resilient way, but that's often very difficult, especially if you think of something like processing keystrokes. That involves interrupts, that involves code execution paths that you only execute if you process a keystroke. So probably it's really hard to eliminate that leakage. If you have a safe software implementation, this does not mean that you have a safe execution. You can still get data leaked from the software implementation. And the leaks come from the hardware because the software runs on hardware, and hardware is not perfect. So we will talk about leakage from hardware. We can attack a lot of different things with that, crypto or other sensitive information like keystrokes. If you imagine I type a password and you know the length of the password, or you can even single out some digits, that would be a bad thing, and mouse movements might also be bad to observe if you can do that. We will start with timing differences. All the attacks I do start with the timing differences. So you see one case and the other case, and you observe that you have a different runtime for those two cases. So here we have cache hits. They are mostly around 75 cycles in my case, including all the measurement overhead, of course. But cache misses are clearly apart from that, so they are mostly above 200. Actually, there's not a single case that is below 200. So saying, if I want to distinguish a cache hit from a cache miss, everything that is below 200 is a cache hit. Perfect. Perfect distinguisher. Caches work like this. You have multiple cores. The level 1 and level 2 cores, they are small and they are private. And you have a large level 3 cache, which is shared among all cores, and it is inclusive. That means everything inside the level 1 and level 2 caches is also inside the level 3 cache. And it looks like this. So we have a cache line in level 1, in the level 1 cache, and it's also in the level 3 cache. And if we now evict this data from the level 3 cache, it will also be evicted from the level 1 cache of the other core, which gives us a power to remove things from a remote core. We can throw out data from a core that we cannot access. The next property that we are going to exploit is that caches are set associative. If you work on a lot of congruent addresses, then they would map all to the same cache line, right? So nowadays we don't have lines anymore, but they are sets, and they have multiple ways that are equivalent, and we can just use one of those ways. And a replacement policy decides which of the ways is evicted and where the new one is stored. And this is all we need to perform our first attack. This is the flush and reload attack, a very powerful attack. It's also the attack primitive that I used in the demo I just showed you a minute ago. So the flush and reload attack works like this. You have an attacker program running and a victim program running. They have a separate virtual address space, and they use the same shared library. A shared library is shared in memory, and because a cache is based on physical addresses, it's also shared in the cache. So if it's cached for one of them, it's cached for both. Now the attacker will flush the code of the shared library from the cache, and then it will reload, then the victim will or might load the data, and if the attacker will now try to re-access this location, the attacker will see that there is a cache hit, although the attacker just flushed the data, so there shouldn't be a cache hit, right? So the attacker learns that the victim just reloaded the data into the cache. And you can do really nasty stuff with that, for instance, an RSA. If you have an RSA encryption with a typical square and multiply routine implemented for the exponentiation, you can derive almost 100% of the key bits after observing a single encryption through the cache. For AES, we can obtain full key recovery in an asynchronous attack in 30,000 decryptions. That's just a few seconds. Also, what I've just shown you earlier, cache template attacks allow to automate these attacks. So I just say I want to have this event and I want to attack this file or this library, and it will automatically find you the addresses which leak this information on this event. Now, flush and reload requires shared memory. If we don't have shared memory, we can still do a similar attack exploiting the set property, that the cache works in a set associative way. And here the attacker fills the entire address, the entire cache set, which addresses from its own address space that are not shared. And now if the victim does some computation, for instance an AES encryption, it will replace ways in this cache set. And as the attacker re-accesses the entire cache set, the attacker will observe that some of the memory accesses are slow, and there the victim has replaced some cache lines. And you can do, again, very powerful attacks with that. We have seen attacks on El Gamal, full key recovery in 12 minutes. We have seen attacks from JavaScript, because now you don't need the flush instruction anymore, so we can do the same in JavaScript. What are the challenges? You need addresses that are congruent in the cache, and this is a bit difficult because we don't know how addresses map to the different slices of the different cores, and also without any privilege, typically you cannot get physical address information on current on current Linux systems, for instance, without having root privileges. And also you need to know in which order to access them, which I will come back later to. Okay, let's. This is probably the most difficult problem, but it has already been solved, so we can address also that part later. Just before we start on the prior and probe stuff, I will just present you one more attack that is related to flush and reload, that is flush and flush. And it's based on the observation that the flush instruction already leaks whether something is in the cache or not. And the advantage now is that if we flush something from the cache and find that it already was in the cache, then it's fine, we flushed it from the cache. If we flush it from the cache and it was not in the cache, we also did not have any cache miss. We did not reach the DRAM. So this attack is much faster, and it's also stealthier because it doesn't cause any cache misses. So it's a new attack, and it pretty much works the same as flush and reload, again through this inclusion property. We flush something from the last level cache, it's removed from the local core. Yeah. This will be slow because it has to be removed from the local level 1 cache, and otherwise it would be fast if we just flush it from the last level cache and nothing is there. So this has also, the CL flush instruction also has some other timing leakage. It tells us, so this is hit and miss on different platforms, but we will also see later that it has a second timing leakage. Just to compare flush and reload now with flush and flush. So flush and reload works like this: cached, then we flush, then we reload, and we observe that it was a cache hit, although it shouldn't have been. And for flush and flush, we do the same. First it's cached, then we flush it, and then the victim reloads it, and then we flush it again, but we observe a high execution time because it had to be removed from the cache. Now for the other timing leakage that we have in the flush instruction, we have these different slices in the last level cache, and accessing your own slice is faster than accessing a remote slice. So this leaks on which slice you are running if you know the function, or if you know on which core you are running, it leaks information on the mapping function that maps physical addresses to slices. And we can use that to reverse engineer those functions. That has already been done, and it works really fast. Something else we worked on was we wanted to also perform all these attacks on ARM CPUs because that it was for a long time it was not known whether this is possible, and the reasons were that on ARM you don't have a flush instruction on older ARM CPUs. The replacement policy is not really well predictable. Also you don't have RDTSC to get cycle accurate measurements, and the last level caches are usually not inclusive. This changed with the most recent ARM CPUs, but for older ARM CPUs, they are not inclusive. And also, you can have multiple CPUs. On modern smartphones, you have multiple CPUs that have separate caches. And still, we were able to implement all these attacks because caches are coherent. They will try to be coherent, and they are. And that's why we can still perform these attacks, even cross CPUs, and we can build covered channels with up to a megabit of throughput. This is 2 to 3 orders of magnitude faster than previous work, so we can send 1 megabit per second from one Android app without any privileges and permissions to another Android app. So one might have access to your contacts and send it to another app that has access to the internet, and then all your contacts are on the internet within a second, and you are not aware why that happened. Side channels are also possible. We can monitor taps and swipes just as accurate as the keystrokes I've shown you before. We can also attack crypto implementations. If you have heard of Bouncy Castle is really, you might want to switch to something else. Bouncy Castle still has an AES-T table implementation as the fast implementation. So if you want the fast AES implementation in Bouncy Castle, you will be insecure. So what about other caches? There is more than just data caches in CPUs. And recently, we investigated that, and yes, they leak too. All caches leak. It's always the same. Branch prediction caches leak. And we just looked at something more, the address translation caches. And here we found something in the Intel manual where Intel was being over-specific. So they said things that they should not have said, probably. So using prefetch, this is just copied from the Intel manual. Using the prefetch instruction is recommended only if data does not fit in the cache. Okay, so what if I do it although the data does fit in the cache? I'm not sure. Use of software prefetch should be limited to memory addresses that are managed or owned within the application context. So what if you do it on a memory address that is not owned within the application context? And they even get more specific. Prefetching addresses that are not mapped to physical pages can experience non-deterministic performance penalty. Okay, so not mapped to physical pages, non-deterministic. I would wonder if Intel really can have non-determinism in their CPUs. So probably it's deterministic. They just don't want to explain what it is. So finally, on the last point, I don't have that on the slide now, they say, if you access the null pointer, this will cause a very long performance delay. And this is not really non-deterministic if they can say for the null pointer, it takes very long. So probably they think, yeah, I should not have said that. Okay. So prefetch instructions are somewhat unusual because they are hints. The CPU can ignore them, and because of the way they are intended, like you iterate over an array and you have one loop ahead, you have your prefetch instruction, and then, of course, you will prefetch past the array, and usually it might crash. So they thought we should not really make the prefetch instruction fail in those cases, so it should just not fail. It should never fail. This is a bit weird. And the next part is, if I run the prefetch instruction on invalid addresses or on inaccessible addresses, like kernel memory addresses, on purpose, they cannot fail. So they have to do something. They cannot just fail like that. And the nice part on x86-64 is, or generally on x86 is, you can put the kernel wherever you want. You can put the kernel to the null pointer, you can let it start there, you can put it to -2 gigabytes or -1 gigabytes. You can put it wherever you want. And this causes a lot of trouble here because the prefetch instruction cannot know where the kernel is. So it has to do some translation to find out whether it actually should prefetch the kernel now. So the address translation on x86-64 is a bit complex because you have those 48-bit virtual addresses and they translate to something like 52-bit physical addresses, and you have multiple layers of translation tables. Those tables are each 4 kilobyte in size, and if you would access a single memory address now, you would have to go through all these translation tables. This would be really slow. So Intel introduced another cache hierarchy. So here we have a cache hierarchy that is again specific to the cores. And the lookup direction, I found this part really interesting because the lookup direction is inversed to the previous lookup in the real page table. So we start in the instruction TLB and the data TLB, and if we find an address there, then we can stop there. If we don't find it there, we have to look it up in the page directory entry cache. If we don't find it there, we go to the next level, and finally in the PML4E cache, we can look up whether we have a PML4E entry. And if it's not there, we have to go to the page tables in DRAM, and this will be slow. So as further down we have to go, it will get slower. So on modern systems, modern operating systems, it's usually organized like that. You have the user space and the kernel space, and the context switch just switches to the kernel space, but the kernel space is always there, and it's only inaccessible through permission flags in the page tables. Now, as you could guess a kernel address, in earlier attacks we have seen that, you could exploit a kernel vulnerability if you guess the right kernel address. And they have tried to prevent that by introducing ASLR, so now kernel and drivers are at randomized offsets, and this tries to mitigate return-oriented programming attacks and stuff like that. But if you leak an address, ASLR is basically defeated because only the offset is randomized. Also in modern operating systems like OS X, Linux, BSD, or even in Xen, you have a kernel direct physical map. This maps the entire physical memory into the kernel address space. So for every page that you have in your user space, you also have one page in the kernel space that maps exactly the same location. And we will exploit that later on. So we performed multiple attacks with that. The first attack was on a kernel driver on Windows, and here you can see the minimum about there. This we called a syscall, and we checked with prefetch how long it takes to prefetch an address, and then we found that if we executed the syscall and prefetched the right address, we just found out which address was used by the driver. So this is the address that we targeted that is part of the driver. And as we can run this experiment on our own computer, we can compute the offset to the start of the driver and basically have learned the start of the driver and defeated a KSLR. Another attack works by jumping directly to the direct physical map, because there is this physical map, and if you cannot jump to user space, or if you cannot put your return-oriented programming stack into the user space, then you can just get the physical address and jump to the direct physical map instead. This is known as return to dir direct mapping attacks. And if we prefetch kernel addresses and now check the latency of accesses on our user space address, we will get a very clear image showing the correct translation from the physical address, from the identity mapping to our virtual address in user space. Beyond cache attacks, we have other leakage in system that I also want to talk about. First, rowhammer, where we have leakage from DRAM cells, so actually really the charge from the DRAM cells leaks physically, and for the second part, DRAM, again, that will be a side channel leakage. So how does DRAM look like? We have today modules like this. They typically have several chips on them, and we typically have multiple of them in our computer. So here we have a 2-channel system, and these DIMMs typically have 2 ranks, and then we have the chips on these DIMMs, and the chips are further divided into banks, and these banks are further divided into rows, and these rows contain the actual bits that we store in the DRAM. Now, to access a row, we need to copy it to the row buffer. So if we want to read something from a row, we activate the row, we copy it to the row buffer, and then we can transmit the row buffer to the memory controller in the CPU. Now, DRAM leaks charge over time, so we need to refresh DRAM all the time, constantly, to refresh the cells so that they don't lose their value. If we don't refresh them, they would lose the data just by themselves. And we found that, or other researchers found, and we built on their work, that cells leak faster upon proximate accesses. And this allowed to implement the rowhammer attack. The first was presented in 2014, and then the Google guys developed the first practical exploit from that in early 2015. We worked on the same topic and tried to make the rowhammer attack work without flushing the memory from the cache. Because to reach DRAM, you have caches in your CPU, and everything that you access will be cached. So to access the DRAM, you need to flush things from memory. And that is how the first rowhammer attacks worked. They flush the data from the cache, and it will go back to the DRAM. And then as they reload it, so basically just as in the flush and reload attack that we've seen before, they reload the data from the DRAM bank, and there they activate the DRAM row. So here we access two different rows in the same DRAM bank. Okay, so as we do this repeatedly, after a while, we have had enough proximate accesses that we will have a bit flip in the row that is between the two rows that we accessed. How can we do rowhammer without CL flush? Why do we actually want to do that? Because we have this root exploit from Google. Why don't we just use this? So we thought it might be really nice to have a rowhammer attack from JavaScript, and there we don't have a CL flush instruction. And our idea was to just use regular memory accesses, and we can apply the techniques that we know from cache attacks already. Rowhammer, prime and probe style. It should work. So in theory, it would look like this. So we do our prime and probe attack, which replaces all the ways in the cache set and evicts the data that we wanted to evict, and then we reload it from the DRAM. Okay, then we repeat this over and over again, and then we will have a bit flip. So much for the theory. There were quite some problems while developing this in practice. Okay, so we have two things that we need for rowhammer. As I said before, we need uncached memory accesses. But the other thing that we need is we need to be fast. It's a race against the next row refresh. If we are too slow, we can't have a bit flip in DRAM. So we need to optimize both the eviction rate and the timing. And then we came up with 4 challenges. First, how to get accurate timing in JavaScript to measure whether our eviction is fast enough. That's actually easy. We can just use JavaScript functions for that. How do we get physical addresses in JavaScript? I will come to this in a minute. That's also something we solved in a previous work already. Which physical addresses should we access? A colleague of mine has solved this previously before we started working on that. And then in which order to access them. In our work on rowhammer.js, we found out that this is the crucial point to perform rowhammer in JavaScript. So how do we get the accurate timing? In JavaScript, you have the window performance now function, which returns a really accurate timestamp. Back when we worked on the attack, it was still accurate to nanoseconds in Firefox. A recent patch rounded it to 5 microseconds. That was by the end of 2015. Our attack still works because we do millions of accesses and measure over these millions of accesses, so 5 microseconds is still accurate enough for our attack. Physical addresses and DRAM, so we have multiple connections to physical addresses now. So we have a mapping from physical addresses to DRAM, we have a mapping from physical addresses to the cache, and we need to connect physical addresses with JavaScript. And physical addresses and DRAM, there is a fixed map similar to the map from physical addresses to caches that maps physical addresses to DRAM cells. And it is undocumented by Intel, of course, because they found something that they think is very performant, and they don't want everyone to know what this function is. It has been reverse engineered for Sandy Bridge by Mark Seaborn, and we reverse engineered it in a recent paper for basically all architectures. Our reverse engineering approach runs in software, and it also works on mobile phones, for instance. How do we now get physical addresses in JavaScript? The nice part is we don't need the full physical address. We only need the part that maps to the row. And if we look at how the operating system allocates memory, JavaScript will just use malloc. And as you allocate large arrays and start filling them, the JavaScript engine will just do these memory accesses, and the operating system will allocate 2 megabyte pages for you. And as we know, the last 21 bits of physical addresses are the same as the last 21 bits of virtual addresses for 2 megabyte pages, are the same as the last 21 bits of JavaScript array indices in the case of 2 megabyte pages. So it's a good idea to give physical addresses to JavaScript, right? So we have DRAM rows now on those 2 megabyte pages. A DRAM row is 8 kilobytes in hardware, but because of the way how the addressing functions of DRAM work, these 8 kilobytes are scattered over regions of 128 or 256 kilobytes. So multiple DRAM rows from multiple banks are interleaved there. So we have multiple rows there that we can use for our hammering, and we also have multiple congruent addresses that go to the same cache set, so we can also use 2 megabyte pages to evict things from the cache. So how do we actually evict things from the cache? And that is where we did something different than previous work. Previous work used LRU eviction there, and LRU eviction the assumption there is that we can just access n addresses from the same cache set to evict an n-way cache set. And it works like this. So you have some timestamps, and you always evict the oldest one, and at some point the entry that you wanted to evict is evicted. Now, for modern CPUs, that is not true anymore, and if you would try it, you would only have a success rate around 75% or even worse. And you could, of course, do more accesses. After some number of accesses, you will be successful, but then you will be too slow. And we started writing down eviction strategies in an organized way that looks like this. So we have set size defined, we have a number of different addresses per inner access loop, so we access addresses, different addresses, and we access them multiple times. So C is the number of repetitions of the inner access loop. So you see this all interleaves, and we will have multiple accesses to the same address. So if you would have a pattern like 2214, you would access address 1, then address 2, then address 1, then address 2 again, then address 2 again, and so on. So you can see this directly maps to this loop. Also, the older eviction strategies can be represented like that. And if we look at our strategies now, so the 11117 is the strategy that has been used in previous work mostly, and it performs 17 memory accesses. We compare it now to a strategy which performs accesses to 20 different addresses. And as you would expect, the eviction rate for the first is not good, but for the second one it's good. But at the same time, the execution time of the second one is low. And now I will compare this to a strategy that we found instead. We will perform 2 accesses to every address, to all of these 17 addresses. We perform 2 accesses. Now, you might expect that the eviction rate is higher than in the case of 17 accesses, right? But it's even higher than in the case of 20 accesses. So we access fewer different addresses, but have a better eviction rate. And at the same time, we perform 34 accesses instead of 17, but we are much faster. More memory accesses makes it faster. And I can even put this one step further. We will look at this strategy, which performs 64 memory accesses. And here we have even a higher eviction rate, and it's even faster. So 64 memory accesses are faster than 17 memory accesses. More memory accesses, smaller execution time. How does this make any sense? And there is a really simple explanation. The way the eviction strategy works is optimal for some cases and least recently used access behavior is not amongst them. So if we access something in least recently used behavior, we will mostly have cache misses. So it will look like this. So we have two strategies here, we compare them, and in the beginning we have our two cache misses that we want to have for our row hammer attack, and then it continues with cache hits and cache misses. And as you can see, the second strategy is much more optimal for the replacement policy that is implemented in the CPU, and therefore it is much faster because it has much more cache hits. This was actually a thing that was really hard to convince people reviewing our paper of that this is actually true. They were like, how can it be? If you perform more memory accesses, it should be slower. You have done a mistake there. And yeah, the paper was rejected. But later on, we convinced them at another conference. So if we compare the number of bit flips now, so we have here the number of bit flips with the classical row hammer attack with CL flush and our eviction-based row hammer attack in native code and the eviction-based attack in JavaScript. Here you can see that the number of bit flips is a bit lower, but you don't really care about the number of bit flips. You care about whether there is a bit flip at all. So if you have a bit flip in native code and with CL flush, you will also have a bit flip in native code with eviction. That's probably always the case. For JavaScript, it's a bit more complicated because JavaScript can be a bit slower, and also it's more difficult to find the physical addresses that evict the addresses. So there we required a higher refresh interval set in the BIOS. This is actually DRAM specific, so for another DRAM, the attack in JavaScript might work. On this laptop, the attack in JavaScript works out of the box. But it totally depends on the DRAM that is built in your system. So the takeaways for rowhammer are cache eviction is fast enough to replace CL flush, and independent of the programming language, you can perform rowhammer attacks, and this is basically the first remote fault attack from a browser. And I have put a citation here of a recent paper by Eric Bosman et al. They combined rowhammer attack in JavaScript with a page deduplication attack, and with that have a reliable exploit from Microsoft Edge to root on Windows, on a fully patched Windows. Okay, so there's no vulnerability in Edge either. So now I will come to the last topic that I want to talk about, and that is drama. That was also something we recently worked on. And here you can see a typical debug output of a double-sided rowhammer program. You can also download that from our GitHub. It's a modification of the Google tool that aims to be a bit more efficient in finding bit flips. And here you can see the number of cycles it took to execute one hammering loop on average. So we do like 2 million rounds of this hammering, and the average execution time was this. So you can see mostly it's around 200 cycles, and some cases are 270 cycles. And actually, only after we have seen times like 270, a bit flip occurs. We have observed that. So it's a lot of wasted time. All the cases where it says 200, this is just wasted time. At the same time, this might tell us something. So we have one fast case and one slow case. And as we know, bit flips can only occur if you hammer rows in the same bank. We probably have found a side channel that tells us whether two addresses are in the same bank. So the other motivation why we worked on these DRAM-based attacks is cache attacks can either not be performed across CPUs or need shared memory. So if you have shared memory, you can definitely perform cross-CPU attacks, but if you don't have shared memory, cross-CPU attacks can be difficult and probably don't work. So this is really difficult because cloud providers now turn to disable page deduplication, which is a good decision, but then we can't perform attacks anymore, which is a bit sad. So if we want to attack the DRAM, we can perform attacks across CPUs. Because DRAM is shared among multiple CPUs. You have a system with multiple CPUs in different sockets on the same mainboard, and they share DRAM. But we don't share memory. So you share the DRAM module, but you don't share memory between the virtual machines. Let's go back to the DRAM organization. So you have these banks and the row buffer. And if you think about it, the row buffer is basically a cache. If something is already in the row buffer, it will be fast. If something is not in the row buffer, it will be slow, because we have to activate another row, write the row buffer back to the, first write the old row back to the, from the row buffer to the actual row, then activate the new row, then copy it to the row buffer, and then we can see the timing differences. So how do we exploit these caches? Basically, yeah, if the row was already opened, we say it's a row hit, similar as a cache hit, and if the row was not opened, we say it's a row conflict, similar as a cache miss. And if we look at the timing here, I just have added to the histogram that I've shown in the beginning. So there you have seen cache hits and cache misses. Now I have divided cache misses into two categories, row hits and row conflicts. And here you can see that there is a small number of cases where we observe a row hit which is faster than a row conflict. And we can, of course, force the CPU to always have a cache miss by flushing memory from the cache. And then we have a side channel attack again. So in this attack, I just show you one example attack because all the reverse engineering, that's all written in the paper. And also we will have a Black Hat Europe presentation on that topic, so you can see it there in more detail. So what we can do is we allocate a large buffer in our attacker program. The victim program runs in parallel. They have no shared memory. Then we might have the situation that both map to the same bank in DRAM, because banks are huge. You only have like 64 banks in DDR4. So the probability that you share a bank is really, really large. And the probability that you share a DRAM row is also large, because DRAM rows are scattered over like 256 or 512 kilobytes. So the probability that you have a 4 kilobyte page in that region and the victim has a 4 kilobyte page in that region as well is really large. And then we just iterate over our own memory and run basically a flush and reload attack on that, but look at a different timing difference, because no one will reload it now, but we might observe the difference that I've shown you before, the row hit, although we shouldn't see a row hit. So it's basically the same as a flush and reload attack, but on the next level on the DRAM. And there we can have, without shared memory, again, a keystroke attack. We just profile the memory, record the row hit ratio for each address, and then pick an address that works. And here you can see the keystroke timing log, and while I entered the Facebook URL in Firefox. So what are the takeaways? Every performance optimization leads to a side channel, unless this performance optimization basically is generic and it always works the same. If it always goes through the same execution path, if it always accesses the same data, then it's fine. But if your performance optimization is based on spatial locality, on temporal locality, on some knowledge of data that is being processed, then it's a side channel. And we can exploit that. Caches leak data. If you have a cache, it will leak data. Today's computers are fast because of these small optimizations. So we have kind of a dilemma here. We don't want to make our computers slow, but at the same time, we want to get rid of the leakage. So if we have to decide between performance and leakage, probably most people will just choose performance and don't care about the leakage. So our prediction for the future is computers won't stop leaking. We will have loads of cache attacks and other side channel attacks on microarchitectural elements in the near future as well. And with that, I would like to end. Thank you for listening, and have a nice day.